Yes. So, good afternoon, all, and welcome to this today's session on Introduction to Process Simulation using DWSIM. This is part of our ongoing webinar series on open source tools for engineering. DWSIM is one of the such tool in open source platform that is available for various process simulations in chemical engineering. So our today's session we are doing under the chemical engineering division. I'll start with my introduction and then we'll take you through what is open source and how we are talking about this technology, and then we will shift to our today's topic on DWC. So I'm Himanshu Bhatt, Secretary at IEI South Gujarat Local Center. I'm also exploring and implementing open source tools at my own startup on mechanical design services and helping all to benefit through open source technologies. So, what is free software and open source? So, when we talk about open source, mostly we have a concept that it is a free software, but it is not only a free software. The major benefit is something different. It I'll just keep you through this development history and all. But the open source means it has its source code available publicly, so that anyone can study, modify, and redistribute it under specific licenses. So various examples of open source tools that are available is Linux operating system, Python coding language, Firefox browser is also an open source, PostgreSQL database, FreeCAD software on which we had done our earlier webinar. So all these are open source tools available. If we talk about engineering analogy, if there is a sealed machine, it is a proprietary software. And if the machine is available with all the drawings and you are able to modify the machine to change its purpose, its functionality, that is how it is related to open source technology. There are various types of licenses in open source, but as a user, we don't need to worry about this. We can just use the open source tools without any license problems. So are open source tools reliable? This is a question which we were trying to answer through this webinar series. So we know that Android, Internet, maximum of Linux servers around 96%. If we go by the statistics, 96% of the online servers are running on Linux. So this technology open source is already reliable. It is proven technology. Coming to engineering, why it struggles then? So it struggles. What we feel is because limited awareness, because of the tools are available, but people are not utilizing it due to awareness, lack of knowledge. There is also a learning curve, like initial setup and workflow can take time. Some softwares are such that they work on Linux or Windows subsystem for Linux. So those terminologies many people may not be aware, and the software utilization remains very low. Similarly, support is not centralized for open source tools. It relies on community forums. So this is again a point where people struggle to implement the open source tools. But as Mr. APJ Abdul Kalam, our chief scientist, the vision for free software movement, in this he had highlighted the importance of open source movement. And today we know that the tools have benefits and we know the constraints. So to break this constraint, today we are talking about DWSIM software. We have our today's speaker, Mr. Priyam Nayak. He is project research scientist from IIT Bombay. His work focuses on process modeling, simulation, optimizing using free and open source tools such as DWSIM and OpenModnica. There is another open source tool which has very good features. We will talk in future sessions if possible. He also has been recognized as outstanding young chemical engineer by Institute of Chemical Engineers for his contribution in chemical engineering field, and he is pursuing PhD with research focus on modeling and optimization of refinery process. So with this introduction, I welcome our today's speaker, Mr. Priyam Nayan, and I also welcome a senior project manager from FOSSI team IIT Bombay, Ms. Payal Mukherjee, to today's webinar. Welcome both of you, and now I hand over the session to you. Thank you. Yes, Payal ma'am, you can unmute and share your views on this.
Yes, yes. So I would like Priyam to talk because he is the main speaker today.
Yeah.
Yes. So I can tell everybody a few lines about FOSSI. So actually, FOSSI, we are developing this project at IIT Bombay, and this project is funded by the Ministry of Education, Government of India. And our vision or aim, why we are running this project since 2009 at IIT Bombay is education for all and employment for all. So we want to empower all the learners, not only the students but the faculty members, the professionals, with the knowledge and the practical hands-on training on free and open source software, so that that knowledge can be used by the learners and also used in their everyday life, like their ongoing projects, their teaching, their research, and anything that they are using on science and engineering field. So this is I have covered this FOSSI's aim in a nutshell, and I would like everybody to, attend all the webinar sessions and probably the upcoming workshops very sincerely, and use FOSS in your offices, in your, in your own startups or wherever you're working. And our team, the FOSSI team from IT Bombay, will always be there for support along with IEI. So once again, we thank IEI for this initiative, and that's all. And from my side, and I'm handing it over to Priya.
Thank you, ma'am. Sir, can you see my screen?
Yes.
Yeah. Okay. So, as the today's topic for this webinar is to give you a very brief to walk you through this tool called DWSIM, which is an open source tool for process simulation. Good evening, everyone. I am Priyam Nayak. I am a project research scientist at FOSSI project at IIT Bombay, and I am also a PhD research scholar here at IIT Bombay. So this is briefly the outline of my today's talk. I'm going to introduce this software DWSIM to you, introduce some features of the software, and then give you a brief demo. And then what activities FOSSI is doing under using this software DWSIM, I'm going to talk about it. Okay. So, and finally, I'm going to also talk about what we have for academia and industry as a part of FOSSI's initiative to promote DWSIM. Okay. So coming to the introduction part, as Pal ma'am rightly said that FOSSI is a project hosted at IIT Bombay, funded by Ministry of Education, Government of India, which stands for Free Open Source Software for Education. We basically train and develop different open source softwares. We also promote different open source softwares, like you can see here: Scilab, Python, eSIM, OSDAC, DWSIM, OpenFOAM. So these are all open source softwares, and they are alternative to certain commercial tools. Like, for example, Scilab is a open source alternative to MATLAB. eSIM is an open source. Or again, eSIM is something which has been developed here at IIT Bombay. It's for electronic simulation. OpenFOAM is a computational fluid dynamic CFD software used, that is an alternative to ANSYS. Okay. OSDAC is a steel structure design, so somebody who is in civil can use OSDAC for steel structure design. DWSIM is a process simulation software which is alternative to Aspen Plus, Aspen HYSYS, Pro2, right? So like this, these are all different offerings that FOSSI have, different softwares that FOSSI have. Coming to by the way, before I move to DWSIM, just to let you know, this is the FOSSI site, fossi.in. Okay, and you can see that as Himanshu sir was also talking about the vision that our former president Dr. Kalam had, and he has spoken a lot about how we all should, work towards, work using the open source software, so that it's very unfortunate that in a country of 1.4 billion people, we still rely so much on proprietary solutions. Okay, and that is a very big hindrance to our education actually. That we are relying so much on commercial. Yes, commercial is there when as and when needed, we can use it, but I don't think that should be a hindrance to our learning, to our education. We can definitely rely on these open source softwares, open source tools, learn the software, learn the basics of the engineering through the software, and then probably as and when needed, we can we can easily migrate to the open source to the commercial tools. Okay, but that should not, I don't think that not non-availability of commercial tools should be an hindrance to our learning, to our education. Right, so you can see this is FOSSEE.in is what the FOSSEE's website, and there are different projects that we have. So in case you're interested in any of these, you want to check it out, you can just click on it. For example, if you click on DWSIM, it will take you to DWSIM's homepage that FOSSEE has, and it will tell you the different activities that are available. Okay, so I'll come to this part shortly, but let me first introduce DWSIM to you. As I mentioned, DWSIM is a free and open source process simulation tool that is used for chemical engineering applications. It's an alternative to Aspen Plus, the most commercial and popular process simulation tool is Aspen Plus. So it's a free and open source alternative to Aspen Plus. Here you can build process flowsheet using operations like heat exchanger, heaters, pump, reactor, distillation columns, right? And it also includes several thermodynamic models like Bang-Robinson model, Soev-Redlich-Kwong model, activity coefficient models like NRTL, Uniquac, Unifac. It's a Cape Open compliant tool. I'll again, when I give you the demo, I'll explain you what exactly I mean by Cape Open compliant, and this is a very big thing to for a software to be Cape Open compliant. So when I give you the demo, I'll explain you what exactly is Cape Open compliant. And as unlike commercial simulator, DWSIM doesn't have a license cost, so that makes it highly suitable, especially for students, for teachers, for the colleges which cannot afford a simulation tool. They can definitely make use of it, integrate this software, integrate this tool along with your curriculum, and you can use it. We extensively use this tool here at IIT Bombay. Even after having subscription of Aspen Plus, we do use DWSIM. We rely heavily on DWSIM in all our courses, starting from process design 1, process design 2. All our courses, we rely heavily on DWSIM tool. Okay. And as I said, being open source, it promotes a lot of transparency. You can customize the tool. That's the best advantage. Being open source, that you can customize it as per your own requirement. You can integrate it with other tools like Python for automation, for optimization. I heavily use DWSIM. As a part of my research, when I have to do optimization, I integrate DWSIM with Python. So that is another, advantage of being the software being open source. And as I said, it will help you to bridge the gap between the theoretical chemical engineering knowledge that you have and practical process simulation. Okay, so that's what DWSIM is all about. By the way, DWSIM is not developed by us at IIT Bombay. It is developed by this engineer called Daniel Wagner. So that's what the name DW stands for, Daniel Wagner. He is a chemical engineer at Brazil. I forgot his organization name, but yeah, he's a chemical engineer at Brazil, and we do work very closely with Daniel on DWSIM actually to give constant feedback on different errors that we face, different issues that we face. Okay. Now coming to this, I wanted to pose this question because very often people think that whatever, people don't understand what is the capability or what is the purpose of a process simulation tool. And that is the reason I have written this, that what do you think is the difference between design, simulation, and optimization? From a process engineering perspective, what do you think is the difference between these three? And it is very important to understand it, because unless you understand what is the base capability of a process simulation software, we don't really, people don't really do justice to its use. Okay. So that is the reason I wanted you to understand what is the difference between these three terms: design, simulation, and optimization. Basically, if you have a process flow sheet and you know that, okay, these are the certain inputs that I have. For example, if you want to produce, let's say, cumin, you know that you can produce cumin from benzene and toluene. All right. So you know that if I mix this much kg of benzene and this much kg of toluene, I'll produce this much kg of cumene. But then under what operating conditions should that plant be operated? Should the reactor be operated? What will be the size of the heat exchanger? What will be the size of the distillation column? When you try to find all these answers as to what are your operating conditions, what are your unit parameters. When I say unit parameters, I mean to say the size of the equipments. So if you're trying to do this kind of exercise, this is typically a design problem. Now, if you know your input, if you know that, okay, this is my plant, reactor size, this is my reactor volume, this is my reactor length, this is my heat exchanger type. If it is a shell and tube heat exchanger, this is my heat exchanger type. These are the number of tubes in my shell and tube heat exchanger. This is the shell side. This is the tube side. If you have a distillation column, these are my number of stages in a distillation column, or this is the packing that I'm using in a distillation column. You have all this information with you, and then you put them in a software and try to find out the output. That is typically a simulation, and that is what exactly these softwares, DWSIM, Aspen Plus, Aspen HYSYS, are supposed to do. They are not built for design purpose, they are built for simulation purpose. Therefore, when you come to simulation, when you come to the software, DWSIM or Aspen Plus for that matter, you should know that you should have these inputs first in hand if you want to use this software. Okay, if you want to design a process plant, if you want to simulate even a certain unit, you must have all this information: your input stream information, your operating conditions information, your unit parameters, your size of your equipments. You must have all of these, and then only you can use them in a software, in these softwares, DWSIM, Aspen Plus, and find out your output. Does it mean that this kind of softwares we cannot design it? No, there are certain design problems that we can also do in these softwares, but not everything cannot be designed in these process simulation softwares. Okay, so therefore, we still today rely on our hand calculation, pen and paper calculation to do the design. And once you have the design with you, you can probably put them to a simulation tool and perform the simulation. Okay, and as I said, optimization is definitely another, it's a very important part of our chemical process plants today, because if you always want to increase your productivity, increase your profit, and then it is not always possible to do different runs on pilot plant. Instead, you can have a digital pilot plant, a digital twin of the plant in your system in these softwares, and you can perform optimization, and you can arrive at a best design, best operating point. You can maximize your profit. Right. So with that introduction, let me take you to the different features that DWSIM has. Okay. So this is what the landing page of DWSIM looks like. There are different, as I said, like what Aspen Plus can do, a lot of things can be done using DWSIM also. The first is obviously process modeling. Earlier, DWSIM was used only for steady state process simulation, but now slowly it has also been tuned, and it has also been designed to perform dynamic simulations. It cannot perform it to the extent to which Aspen Plus can do, but definitely some of the basics can be done definitely in DWSIM. But as far as steady state simulation goes, DWSIM can perform whatever Aspen Plus can also do. Okay, so that's the capability in terms of process modeling. Another important feature in DWSIM is user compound creation or data regression. So the commercial tools that we have today, for example, again I'll keep giving the example of Aspen Plus because that's the most commercial and popular tool that we have. So in Aspen Plus, it has a very huge database of component, right? Because whenever you come to simulate any process, you need the component information. That's where another limitation comes to the software of this DWSIM, that it doesn't have that huge of a database, like a component database like Aspen Plus. But this user compound creation tool is again a very big useful tool to us, where you can actually create the compound in DWSIM and then simulate them further if those compounds are not available in DWSIM by default. Okay, so I'll give you again a demo of this user compound creation tool also, as to how you can create compound using DWSIM tool. Data regression, you can perform data regression to generate binary interaction parameters in DWSIM. Other than that, yeah, you can see that as the feature goes, these are the different unit operations that are available in DWSIM. As I was telling you, orifice plate, compressor, pump, expander, valve. Then you have reactors, different kind of reactors you have. Okay, you have heat exchanger, falling film evaporator, cooler heater, and then different kind of reactors, different kind of columns like distillation column, absorption column, extractive distillation column, shortcut column. So yeah, different solid operations are also present, like filter, centrifugation, solid separation. All these unit operations are also present for solid. So these are the different unit operations that are available in DWSIM. Moving to next, as you know that in DWSIM, or for that matter any process simulation software, in addition to have the components, you must have the support of thermodynamics, because as you deal with different mixture, different component system, different thermodynamic property packages govern those mixture. So yeah, these are the different thermodynamic models that you can see are available with DWSIM, starting from you can see Raoult's law is available somewhere. Yeah, this is the ideal Raoult's law. Peng-Robinson, the famous Peng-Robinson model, which is equation of state model, and then different variations of Peng-Robinson. Similarly, you have Soev-Redlich-Kwong model, another equation of state model. Then you have UNIFAC, the activity coefficient model, UNIFAC, UNIQUAC. You have NRTL, you have Wilson. All these are activity coefficient model. And then also you have thermodynamic models for electrolytes, something like this aqueous electrolyte model. Grayson-Street. So these are the different property packages, thermo property packages that we'll typically find in any process simulation software, and they are also available here in DWSIM. Okay. So these are some of the features of DWSIM. I'll deep dive more detailed into all of these once I give you the demo of the software. Okay. And now coming to the activities that we promote under in FOSSEE under DWSIM. These are the different activities that we have: DWSIM flowsheeting project, DWSIM custom modeling project, DWSIM lab migration project, and then textbook companion project. So the main are the first three that you see: flowsheeting project. I'm not sure if anyone of you have heard this project about, but what we do generally is that we have invited, or we generally tell students specifically that can you take any process flowsheet that is available in any textbook, any research paper, along with some results. They must have been done using some commercial process software, and simulate that and give us that in DWSIM. Okay, so as a part of that project, let me just show you here in the website, in the FOSSEE flowsheeting project, in DWSIM flowsheeting project. So you can see there are about 274 flowsheets that are available actually. You can see starting from some extractive distillation to some production. You can see this is a flow sheet on ethylene oxide production from styrene, like this hydrogen production from biogas, and these are done by students from various places, not only from India, but you can see from across the world. Actually, students have contributed to this project. You can see somebody from Pakistan have contributed. We have somebody from Tehran University has contributed this project. Students from Ecuador, all over the world, people have contributed to this project. And they are available for free download. For example, if you click on this project, it will take you, and here it says that this is the project proposal. I mean, this is a person, Mr. Paresh Rathod from Marwar University. He has completed this project, and you can download the abstract and the DWSIM flowsheet here. Okay, and it gives a reference as to from where that particular flowsheet was taken. So you can see here the references listed for this particular flowsheet. Okay, so this is about DWSIM flowsheeting project. By the way, this is okay. Just as I'm in DWSIM flowsheeting project, let me tell you, if any of you have downloaded the software DWSIM, or if you download the software DWSIM, actually, this is what the welcome page of the software DWSIM looks like. And in the welcome page itself, here towards the right hand side, you can see there is something called as FOSSEE flowsheet. Okay, FOSSEE flowsheets. So all the flowsheet, 274 flowsheet that you actually see there in the FOSSEE's website are also actually are available here as a part of FOSSEE's, DWSIM software. You can see all those 278 flowsheets here. If you want to open any, you can just click on it, and it will give you saying that this is the project and this is the author, this is the institution. And if you say yes, it will just download and open the software, open the flowsheet and the abstract for this particular software. Okay, so this is with the flowsheeting project. Then moving next, we have something called as custom modeling project. Okay, now what this custom modeling project does is that Sometimes there are some specialized equipments that you want to maybe process, you want to simulate, but then it is not available in the software DWSIM. What DWSIM has done or enabled is that you have the feature to model the software by yourself using something called as Python, IronPython or Python.net. Okay, so that's basically Python. So you can actually write your own code for your unit operation if you want. If that is not available as a part of the DWSIM software, you can write that using Python. And I think in today's world, Python is something which everybody learns irrespective of whether he is from a CS background or not. Okay, so yeah, Python is a very, I mean, it's a modern day language that is used widely, accepted widely, and if you know Python, you can write your own custom model. In fact, you can also write using Scilab. If you know Scilab, DWSIM supports writing the custom model using Scilab. So you can see here that people have written codes like cooling tower. People have coded cooling tower, helical coil heat exchanger, counter current absorption tower, packed distillation column, plate heat exchanger. All these things have been coded by different people. They might not be very robust, but then it suits them to it can do some kind of solving. It suits them some certain degree of problem. I mean, some certain degree of, what do I say, capabilities is available with this. So, and therefore they have coded it, they have modeled it and submitted it to us, and we have hosted all those custom models. So this is another activity that we have, which is custom modeling project. Other than this, also we have something called as lab migration project, which is for institutes. That if you have a lab, lab using commercial software like Aspen ICS or Unisim or Aspen Plus or Pro2, we help you to move those labs to DWSIM. Okay, so whatever is the process simulation problem statements that you are solving in those labs using the commercial software, we do help you to migrate such kind of labs using DWSIM. Okay, so that makes your lab commercial software independent. You can use DWSIM, which is a free and open source software, in those process simulation lab. Okay, so these are some of the activities that are there in DWSIM. And with that, now it's time for to give you a demo, because I want to talk more and more about the software DWSIM, its capabilities, and therefore to do that, I want to jump to the software and give you some quick demos of different features that are available using this software DWSIM. Okay, so yeah, let me just open it once again. By the way, you can see here in my screen, let me minimize it once again. Here you can see there are two different icons. So when you install DWSIM, if you do it in DWSIM, if you do it in a Windows machine, you can see two icons will come. One is DWSIM, one is DWSIM cross-platform UI. The one that is widely used is this DWSIM. This cross-platform UI is for Mac. Okay, this is for Mac because Mac doesn't support the UI which is supported in Windows. Therefore, there's a different UI for Mac. But DWSIM can be used in all three platforms, Linux, Mac, and Windows. In Linux also, you will find both these two UI, DWSIM and DWSIM cross-platform UI. In Mac, you will find only this cross-platform UI because the other one is not supported. But the demonstration that I'm going to give you is using this classic UI, the old UI, which is there with DWSIM. Okay, so once you click on this, this is what the welcome page looks like in DWSIM. And you can see you have different samples here, and then there are different flow sheets here. Okay. Now, coming to the demonstration part, when you have to build a process flow sheet, the process steps that you go through are actually typically same in every process simulation software. For example, to begin with, you have to select certain compounds. Then you have to select some thermodynamic package which will govern those compound mixture. And then you select a system of units, and then you move and build your flow sheet. Now, this process remains same throughout every process simulation software. And therefore, as I said earlier, that since this basic process of building a flow sheet remains same, the input that you give also remains same through every software. If you don't have a commercial tool, please learn open source software like DWSIM. Because then if you know that, okay, this is how a process simulator tool operates, all that you have to learn additionally is that how the UI changes with different softwares. Okay, so it's just that the UI is different for different commercial tools. When you compare them to the open source tool, but then the basic steps of doing process simulation remain same across all the process simulation software. Okay, and therefore, to start with, let me give you a quick demo of first one small flow sheet that I want to show you. Okay, so if you want to start a flow sheet, you can say file, new chemical process model. Okay, and then you say next. So there are different compounds here. Okay, so as I mentioned you earlier that the one limitation for this software DWSIM is that it doesn't have a huge database as you see in Aspen Plus or Pro2. But then, as I said, we have the compound creation tool where if you enter certain information, DWSIM will generate the compound for you. It will create the compound for you, and you can use it further in your simulation. Okay. So these are the different compounds that are currently available in DWSIM. Okay, so the demo that I'm going to quickly give you is the process of, again, same that I was talking about, like benzene and toluene giving your, benzene and propylene giving cumene. Okay, and with that, the next step is to select again a thermodynamics, right? So you can see that depending on the compounds that you have selected, DWSIM is actually suggesting you that these are the set of thermodynamic packages that you can work with. Okay, so the one that you see in blue, green ticked, these are supposed to be the suitable package for the selected compound system. The one that you see grayed out, they are not suitable. Okay, but then we should not completely rely on DWSIM or for that matter any process simulation software for the selection of thermodynamic package. Definitely it is a suggestion that it has given, from which I get an idea that, okay, I should use the equation of state model, but we should also have a good understanding of thermodynamic concepts to actually select a correct thermodynamic package. Because it's not only just uh, the the compound, but also the operating conditions that dictate what should be my thermodynamic property package. Okay, so therefore, for example, for this particular compound selected, I can work with either Peng Robinson or Swift Redlich comb. Okay, because it's a it's a hydrocarbon model. The system is a hydrocarbon system, so equation of state model is suitable for such kind of hydrocarbon system. So I've selected Peng Robinson for this. Then if you say next, also by the way, here you can see that what is the phase equilibrium settings that you want to work with. The default is SVLLE, solid, vapor, liquid, liquid equilibrium, or you want to work with VLLE, or you want to work with VLE. Okay, so depending on the kind of phases that are going to be there in your software, you can actually select. I'll leave it with the default SVLLE, although there is no vapor, but although there is no solid, but definitely there will be vapor, liquid. So I'll leave it with the default for now. Then if you go next, sorry, if you go next, it asks you to select a system of units. Okay, for example, something. So I'll just select. So there is standard system of unit like SI, CGS, and English. This is the standard system of unit, and then this C1 to C5. These are custom system of units that are available. Okay, and if you say next, next, and finish, so that way your simulation is configured. So you have selected your component, you have selected your thermodynamics, and now you are ready to simulate your process. Okay, so that's how you configure your system. And once it is configured, so let me give you a demonstration of maybe 2 or 3 quick demonstration I'll give you. For example, let me pick up reactor. Or for a chemical engineer is a reactor. So let me pick up reactor. So you can see here, there are different reactors here: conversion reactor, continuous stirred tank reactor, equilibrium reactor, Gibbs reactor, plug flow reactor. All right, there are different kind of reactors here. The one question that we face is that what is the reactor that we should select for our process? So there are two aspects to it. One is obviously what is the phase or what is the kind of solution that you are working with, that will dictate your reactor type. And secondly, what is the kind of information that you have about your reaction. Okay, so for example, if you only know that, okay, benzene will react with propylene to give cumene, but you don't know the kinetics for that particular reaction, you only know that there will be an 80% conversion. In that case, we work with conversion reactor. Okay, or if you only know, let's say, the equilibrium constant for that particular reaction, then you can work with an equilibrium reactor. But if you know the kinetics, then you can work with either continuous stirred tank reactor or a plug flow reactor, right? So these are the non-ideal reactors that you might have studied in your reaction engineering courses, right? And to simulate this reactor CSTR or a PFR, you need the kinetics for that particular reaction, the rate law, right? So let me demonstrate use of a plug flow reactor here. Okay, so this is a PFR, a plug flow reactor. And you can click on this one. So this stream 1 is the input stream. This is my reactor PFR, and this stream 2 is my output stream. Okay. So if you click on stream 1, you can see here that I have certain values that I need to input, and therefore they are blank, they are white. What is grayed out is something that I cannot enter. Okay. So stream number 1 is my editable stream, which is my input stream. If you click on stream number 2, this stream is completely grayed out, which means that I cannot edit my output stream. Okay. So therefore, whatever I want, I can only see the results of the output stream. I can give input here. You remember the definition of simulation that I gave you initially? I will enter my input stream data. I'll enter my unit parameters and my operating conditions here. Okay, and then I'll simulate to get the result. Okay, so let's do that. So this is typically a high temperature, high pressure process. This production of cumene from benzene and propylene. So let's say I give 150 Celsius and then 30 bar. Okay, and let's say I give 100 kilomoles per hour. So this is my flow rate I have given. Okay, for my input stream. So typically for any input stream, you need to specify certain conditions, some temperature pressure condition, like, as I've done here, temperature 150, pressure, and then some flow rate. Okay, so this is the overall flow rate of the stream. You also need to say that in what composition the compounds go, right? So if you click on this tab, compound amount, yes, if you click on this tab, compound amount, you can specify the mole fraction here. Instead, if you want, you can also specify, instead of mole fraction, you can also do mass fraction specifications. You can, you can specify it in terms of mole flow, in terms of mass flow, all of this. So for example, I want to say that there will be, let's say, 80% benzene and 20% propylene. Okay. So I'm not going into every detail of every click, every number that I enter. I'm just giving you a brief demo because it's not possible to teach you the whole PFR, how to simulate the whole PFR here, but rather to give you an idea, to give you a feel of how these things are done. Okay. So therefore, if you or your college is really interested in learning these softwares in detail, if you already don't know, then please do get in touch with us. We'll be happy to conduct workshops for you. Okay. But yeah, this is just a demo session. So yeah, now I have entered my temperature, pressure, flow rate, composition, all this information. And once I've done that, I want to enter my reaction kinetics. Okay. So where do I enter my reaction kinetics? I can go to settings here under reactions. We have different reactions here: conversion reaction, equilibrium reaction, kinetic reaction. So I want to enter a kinetic reaction because, as I said, conversion reactor supports conversion reaction. If you have information only about the conversion, that 50% conversion of the reaction is happening, then the conversion reaction is to be used. What the information that I have or that I'm going to give is the kinetic information, the rate law, the Arrhenius constants, and therefore I'm going to use a kinetic reaction for this. Okay. So here you can say that, okay, these are the components that are taking part in the reaction: benzene, propylene, and cumene, right? That I've clicked under include. That means that these three reactions are going to participate in this reaction. And then you need to specify what is your base component. Okay, this BC is base component. What is your limiting reagent? Clearly, based on the composition that you have given, propylene is my limiting reagent. And then your stoichiometric coefficient. Okay, so in this particular case, 1 mole of benzene reacts with 1 mole of propylene to give 1 mole of cumene, and that becomes a perfectly balanced reaction. But if you realize, until I have entered the complete stoichiometry, there is certain number that is coming here. Okay, so if some number is being shown here, it means that the stoichiometry is still not balanced. By the way, the stoichiometric coefficient for the reactants are to be preceded by a negative sign. for the products, it's only that particular number. Okay, so when I say -1, I mean to indicate that they are my reactants. Okay, and if I say cumene as +1, it means it is my product. And you can see that once I've entered the correct balanced stoichiometry coefficient, the stoichiometry is said to be okay. That means that my reaction is balanced, because unless you enter a balanced reaction, it will not move forward. It will not allow you to move forward. Okay. And then what is the reaction order? So let's say the reaction is first order or the reaction is second order. You can specify that this DO is direct order, this RO is reverse order. Okay, so it means to say that what is my reaction order. Next, next option is to specify something like phase as to what is the reaction phase, liquid, vapor, mixture. Okay, so let's keep it to be a liquid phase reaction. And then your basis. Okay, so if you, definitely I'm sure that all of you would have done course on reaction engineering. So in reaction engineering, whenever we write our rate law, we write minus RA equals to constant K into CACB, or maybe K into PAPB, right? So the rate law that we define, in what terms? It can be defined in terms of mole fraction, in terms of molar concentration, in terms of partial pressure. So whatever is the term that in which your rate is defined becomes your basis. For example, I can say that here my basis is molar concentration. That means my rate law is minus RA, which is equals to K into concentration of benzene into molar concentration of propylene. And therefore your basis becomes molar concentration. Okay. Similarly, you can specify certain amount units as to what is the unit of that molar concentration accordingly. Okay. And here, coming next, you can see here that, if you want to give a simple kinetics and Arrhenius law kinetics, you can give it here. Like, for example, let me give some number. So this is pre-exponential factor. This is activation energy, right? So you have minus, the rate constant, if you want to define it in terms of Arrhenius, it is K equals to K naught into exponential of minus EA by RT. You know this famous Arrhenius expression. So K naught is what is this A, the pre-exponential factor, and EA or E is your activation energy. Okay. And then finally, the rate units, the term in which your rate units is defined. So let's say I'm defining it in terms of kilomoles per meter cube hour. Okay. So if you do that, this way you can define a reaction. And if everything that you enter is correct, and then you say, okay, you'll see that your reaction is added here. Okay. So I have a reaction that I've added here. Now, after adding the reaction, another thing that you want to do is you want to define your reactor volume, reactor length, all of that, right? You remember I was telling you that when you are designing your plant, in that phase, you basically manually calculate, do the hand calculation, find out what is your reactor volume, what is your reactor length. Okay, so that you do that calculation, and then finally you find out, and then you enter those information here in the process simulation tool to do the simulation. So let's say that I have a reactor volume of 1 meter cube. I don't know what will be the result, but I'm just giving a random number that the reactor volume is 1 meter cube, and then I have a tube length which is of 5 meters. Okay. So you can see that when I entered that number, again, I'll go back. So when it is in green, that means that calculation is happening. Okay. If the calculation, if the simulation is successful, it will turn all into blue, and you can see at the bottom here, you get a message which says flow sheet was calculated successfully. And if the calculation is not successful, if it is not converged, things will be in red. For example, let me see if I can give some number to show you that. Okay, it is simulating. But yeah, the point that I want to make is that if the simulation is not successful, if the convergence is not successful, then this will be in red. Okay. So you saw that it took some time. It took a few seconds to do the calculation, and finally, with that calculation. So now you can actually go and see your results. For example, if you go to conversion, it will actually give you that what is the amount of conversion here. What is the benzene and propylene conversion? So 14% of benzene has been converted, and 58% propylene has been converted to cumene. So these are the conversions for benzene and cumene. Okay. Similarly, if you want to look into the profile, if length of the reactor, you can actually see that. Okay, let me just show you that here. I'll say insert a chart. Okay, and in that, tell me the concentration profile. Okay, So you can see here, this is what the concentration, this is how the concentration is changing along the length of the reactor, right? This is for benzene, this is for propylene, and this is for cumene. Okay. Similarly, if you want to see, let's say how the temperature is changing. Okay, if you want to see the temperature profile, you can see that. This is a exothermic reaction, so the temperature is increasing. Sorry, the temperature is increasing. So all this profile you can see. A tool which is typically available in all the process simulators is available also with DWSIM. Okay, so this is how you simulate a reactor in DWSIM. Now, how much time do I have? This is a reactor simulation. Another thing that I was talking to you was earlier, that Cape Open compliant. Okay, the Cape Open compliance thing. Now, what do you mean by Cape Open compliant? CAPE is basically, CAPE stands for Computer Aided Process Engineering. So when you design or when you develop a process simulation software, if you develop it by following certain CAPE Open standards, there are certain CAPE Open standards. This CAPE is particularly is a organization, Computer Aided Process Engineering. It's an organization which defines certain standards for developing a process simulation software. Now, if you develop your own process simulation software using those CAPE Open compliant features, then what happens is that if there are two softwares, A and B, and if they are CAPE Open compliant, they can interact with each other. They can exchange and interuse each other's unit. For example, here in column, you see something called as ChemSep column. Now there is a software called ChemSep. Okay, ChemSep is a completely separate software. It's not a free software. It's a commercial tool, but then a certain version of that software is also free. Okay, so ChemSep is a different software which is a CAPE Open compliant, and again DWSIM is also a software which is a CAPE Open compliant. Now, what advantage does DWSIM have being CAPE Open compliant? It can actually use the ChemSep's column in DWSIM. ChemSep software specializes in column, okay, in different columns. For example, reactive distillation column, extractive distillation column, pressure swing distillation column, different kind of columns that you come across, separation columns that you come across. ChemSep is an organization, is a process simulation software that specializes in that. DWSIM, also being CAPE Open compliant, can actually make use of ChemSep's column in DWSIM without going to ChemSep. Okay, so that is what the advantage of a software is being CAPE Open compliant. I hope I have been able to explain that. If not, please let me know. I'll once again try to re-explain it to you. Okay, so similarly, DWSIM can actually use the thermodynamics of ChemSep also, because ChemSep is CAPE Open, DWSIM is CAPE Open, so it can actually use ChemSep's thermodynamic in DWSIM. So if you see here, if you remember when I was showing you the thermodynamics, there is something called as CAPE Open. Okay, so this CAPE Open is basically, it can make use of any software's thermodynamics which is CAPE Open. Obviously, there are certain constraints like that software has to be installed in DW in this particular machine and all of that. But given all you satisfy all those criteria, you can make use of other software's unit in yours also. Okay, so this is a demonstration of a reactor. Let me show you the tool that I was talking about, which is compound creator tool. Okay, yeah. Wait. Okay, what I'll do is create new compound. Yeah. So you see, I went to the home screen and there was this option called create new compound. Okay. Now, if you have certain component which is not available as a part of DWSIM, okay, then you can actually create those compound. How do you create them? There are different options. Firstly, what you can do is, you can, if you know that, okay, that particular compound is available in some online database. For example, the software DWSIM is actually allowing you to import certain compound from these online databases like KDB and Cameo. Now, this Cameo is another online database where a lot of components are available which are not available in DWSIM. Okay, so if you just enter the CAS ID for that particular compound, it will actually fetch that compound into Cameo. Okay, so let me just quickly search. For example, I know benzene is already present, but I'm just trying to give you a demo, and for that purpose, I'm just trying to fetch this compound benzene. So this Cas ID of benzene is this, okay, 71432. So let me just put it there and say next. And you can see that if that particular component is available in Cameo database, it will give you this, it will say that, okay, benzene is available, say next. And this information of benzene is actually available with Cameo, okay, in the Cameo online database. And if you say import, you can see that the information of that particular compound, in this case benzene, is now imported. And if you go to the constant properties, you'll see all the properties is now imported from Cameo database to your DWSIM. Okay. What happens if that particular component is not available in those online database? Okay, what do you do in that case? In that case, you rely on something called as group contribution method. I'm not sure, I don't know how many of you have heard of this method called group contribution method, but typically what you do is, if you have a component, let's say if you have something called as something as simple as ethane, okay, so it's CH3CH3, so it's 2 CH3 straight CH3 unchanged CH3. You just define that, okay, how many such small functional groups of that compound are present, okay. So if I say 2 CH3 here, it will actually calculate the constant properties based on that number that I enter here. Okay, let me demonstrate this to you so that you can understand it better. I'll say create new compound. Yeah. So let's say I'm defining the molecular structure of a compound. Okay. So let's say there is 1 or 2 CH3, there is 1 CH2, and then there is 1 CH. Okay. And then let's say we have some CH3 which is attached to an to a benzene ring, something of this sort. Right. So if you define the functional groups of your component, functional groups that are present in your component, based on those functional group, actually, you can see here that the properties are getting calculated automatically. You can see here, enthalpy of formation, Gibbs energy, boiling point, critical temperature, critical pressure, all these are getting automatically calculated based on the molecular structure. So if you enter one, again, if you change something, you'll see that these values are changing. All right. So that means that this tool enables you to build your own compound if you don't have that by default in DWSIM. But if it is available, well and good. If it is not, you can make use of this tool. Okay, so this is another feature that I wanted to demonstrate. Other than this, there are different analysis tools. For example, you can perform sensitivity analysis. You can perform optimization also in DWSIM. Okay, if you want, let me show you some of the utilities. If you want, you can, do this phase envelope, for example, a binary phase envelope. Okay, so a binary phase envelope between benzene and propylene. Okay, you know what is a binary phase envelope, I'm sure. A TXY curve, a PXY curve, right? A XY curve. So all these can be, you can do all this. This is between benzene and cumin. So different utilities are available. Same way, what other utilities are available here? You can also draw a ternary phase envelope, and then you can do a valve sizing, pressure PSV sizing, pressure safety valve sizing. You can do a vertical vessel sizing. Okay, so all those facilities are also available in DWSIM. Yeah. So with that, I think I'll stop with the demo for now. Okay, because we are running. We'll be reaching the time. So we have to close also. So yeah, moving on. Actually, installation. This is again. This installation guide is available in DWSIM's website, in the FOSSEE website that I've shown you here. Here under downloads, if you go, the step-by-step manual on downloading DWSIM is available. So in case you want to see it, you can actually see. It's pretty straightforward. For Windows, it's very straightforward. typically like any process, any software that you install on Windows, you have to go next, 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 next. If you just keep doing it, it gets installed. So it's very much easy to install it in Windows. In Linux, before you install, there is certain mono framework that you have to install, which I have, which is clearly mentioned here. So if you want to install in a Linux machine, you just install this mono project first, and then you can do the installation. The process is mentioned. For Mac OS, there is no installation. In fact, it's just that the app directly comes, and if you just open the app, I mean, if you download that app and open it, DWSIM will run on Mac OS. So there is no need of separate installation. There is an app that comes if you go to this website. Okay. So this is a site which hosts the DWSIM download files. So based on what is the software that you have, Linux, Mac, or Windows, it will download accordingly. So that's with the installation. Moving next, actually, I want to talk about what we have for to offer to industry and academia. If both the audience are present here, specifically for to begin with academia, as I said, you'll have free access to this software first of all, and it's a very lightweight software. Actually, I don't know how many of you have used Aspen Plus, but actually Aspen Plus is pretty much heavy. It's the installation file size itself is some 10-12 GB, and once you install it, it takes 30 GB of your system. And on top of that, if you want to run it properly, you need to have a good RAM capacity at least. But compared to that, DWSIM is actually very lightweight software. It takes about 200. I mean, the installation file is about 200 MB, and if you just install, it takes hardly a GB of your space. So that way, you can actually work. I mean, it is very easy to install on every system, and the student can use it on their laptop itself. Also, no license, so that's another advantage. If you have any courses like thermodynamics or courses on separations, design, we can help you to actually frame your courses or help you to select some problem statement where you can actually incorporate DWSIM in your courses. Okay. So for example, in IIT Bombay, you have a course called Chemical Process Design, where we teach the students how to design reactor, how to design distillation column. So when they do that, they also side by side do the simulation exercise. So once they have designed a column, once they have designed a reactor, they also use that design to simulate it. Okay, and they do that using DWSIM. Okay, so we can help you to come up with similar teaching support. Obviously, as I mentioned earlier, it's open source learning. So therefore, if it's open source software, so you can customize the software as per your requirement. But for that, you definitely need some kind of programming background and a good programming background. Okay. If you have a process simulation lab in your institute, which runs on commercial tool, we can definitely help you to migrate that to open source tool like DWSIM. For industry, if you want to simulate your plants, if you want to have a preliminary process design analysis of your plant, we can help you to come up with a simulation of your plant. You can also help you to look into the optimization of your plant by integrating it with Python. Okay, so that's a very cost-effective tool, and definitely you can do the skill development for the engineers who work in your plant. Okay, so that is what we have to offer. In addition to this, as I already mentioned earlier, that we have different activities that like flow sheeting project and custom modeling project and lab migration project. So you can also contribute to those projects as well. Okay, and we also run year-round different semester fellowship. I mean, different internships and fellowship programs in FOSSI using DWSIM, using Python in DWSIM. The students who are interested can check those out. Actually, if you go to this FOSSI's website, okay, and in top you will see internships. So here there are different internship programs that happens. One is semester-long internship, one is summer fellowship, and then another is semester-long internship for autumn. Okay, so typically it says when does it start, and you can check out those links here. So we have year-round internship going on actually, and if you're really interested to work on these process simulation tools, you are welcome to write to us. You are welcome to apply, and we'll be happy to actually take you and work together. So with that, I'll stop my demonstration, my presentation. If there are any questions, I'll be very happy to answer. This is our contact ID, contact-dwsim@fossi.in. If you have any queries, you can mail us here, contact-dwsim@fossi.in. If there are any questions, I'll be very happy to answer. Yeah. Over to Himanshu, sir.
Yeah, so let's see if we have any questions from the audience. I think no, there is no question. Kinshuk sir, is there any question? Can you just confirm and verify? Okay, so fine. Thank you very much, Mr. Priyam Nayak, for delivering this very informative session and concluding rightfully with the summary slide of what it has for the industry and academia both ways. So it was very informative and definitely it will help both the persons from academy to understand the software, learn the software, and for industry to implement this without any special requirements, licensing, etc. So just with this, we thank you and the FOSSI team at IIT Bombay for contributing to this webinar. And I also take this opportunity to thank our Institute of Engineers India, Mr. Kinsuk Sen, for arranging this webinar, and IEI for providing us this platform to share the learnings and to share the knowledge so that everyone can grow with the open source technology. Thank you all.
Thank you.
Yeah, Kinshuk sir, we can
Yes.
close this now.
Yes, yes. Thank you, sir. Thank you. Thanks to the all goes to the speaker for today's session. So informative and so interesting topic is there regarding simulation and its application in both industry and academia. Sir, to the participants, one announcement: our e-certification link is open till tomorrow midnight. Anybody who wants to opt for the CPD certificate, kindly follow the second link in the flyer and please deposit your this amount and certificate will be forwarded by email by next 2 days. Thank you.